This lesson is for section 3.1. This is about critical numbers and absolute extrema. Our goal in this is to find critical numbers and the absolute extrema if we're given a certain interval. So the formal definition of extrema: if the function is defined on an interval containing a point c, f of c is going to be the minimum of f on that interval if that f of c value is less than or equal to all the other y values for any x in the interval. So basically it's just saying that the y value that's the lowest of any of the others, that's going to be our minimum. Our maximum is going to be the y value that is the highest of any of the y values in the interval. So when we have functions, extrema are going to be either high points or low points. So if I have a function like this, this would be an extrema, extrema, extrema. Any high or low points, those are called extrema. The high point on an open interval is called a relative extrema. So this is a relative extrema because relative to the points right around it, it's a high point. This is a relative minimum. So relative maximum, relative minimum. However, I can't call that an absolute minimum because this function continues to go down. So these points here are lower than that point. So that's why this is just a relative minimum and not an absolute minimum. The extreme value theorem says that if a function is continuous on a closed interval from a to b, then the function has both an absolute minimum and an absolute maximum. It must have one of each. Sometimes we can have two values that are going to be an absolute max or an absolute min. I'll show you examples of that. The absolute extrema must occur at the critical number or at the endpoints of the interval. That's the only thing possible. See, for this, the only possibility, if I were to cut this graph off, let's say that I cut it off so that we're only looking at it from here to, let's keep this going down a little bit, to here. See how these would be the high points and this would be the low point. So the high points can only occur at where we have a critical number, which a critical number is where the slope is 0, or at an endpoint. That's an endpoint, so that's lower than this one. So this would be my absolute minimum. This appears to be a little higher than that one, so this would be my absolute maximum. So in this case, we have one absolute maximum, one absolute minimum. So as far as the definition of a critical number, if we have a function and it's defined, if that derivative equals 0, or if that derivative is undefined at a certain c value, then we consider c to be a critical number. These examples are asking us to find any critical numbers for the function. So I have to find where is it that the slope is 0 or where the slope is undefined. So on this one, I'm going to multiply it out. I'm going to take the first derivative, and I'm going to set that equal to 0. So I now need to know what are the values that are going to make this be 0. So I'm going to keep factoring. I'm going to take out a 2x. And so now I have to set each of these equal to 0. So solving the first one, I get just x equals 0. Solving the next one, I would have those critical numbers. Remember, when you have an equation and you're taking a square root, you have to put plus or minus in front of it. So we've got a solution of the critical number at 0. That could be where we have a max or min, or at positive or negative 3 over radical 2. All right, for this one, we have a closed interval. So only over 0 to 2 pi are we looking for our extrema. So I'm going to take the derivative. I have to use the chain rule on this. Here's the reason why. It's u squared. The derivative of u squared is 2u times the derivative of u. which that should actually be a negative sine x. The derivative of sine x is going to be cosine x. So this is my derivative. I have to set that equal to 0. I'm going to factor out a cosine x. Set these equal to 0. So for this one, I have to think, where is it that cosine is 0? That's going to be, where x is 0 is going to be at pi over 2 and at 3 pi over 2. Solving this, I get sine x equals 1/2. So that's going to be at pi over 6 or at 5 pi over 6. So those would be the 4 critical numbers. Those are the places where we might have maxes or mins, but we would have to do more work to figure out for sure. Okay, these examples say locate the absolute extrema of the function on the closed interval. Remember that absolute extrema must occur at either the critical numbers or at the endpoints. So the first thing we have to find are the critical numbers. That's when we take that derivative and set it equal to 0. So we have a critical number at -1. Well, -1 is also an endpoint. So now to find my absolute extrema, all I have to do is plug -1 back into the original, and then my other endpoint of 1. See, the only numbers that go back into my endpoints here when I'm looking for absolute extrema are the endpoints and the critical numbers. So I'm going to plug -1 in. That's going to give me 1 minus 2. That's -1 minus 4. That's -5. Plugging 1 in, 1 plus 2 is 3, minus 4 is -1. So right here, -1, -5 is going to be an absolute min, and 1, -1 is going to be an absolute max. It's impossible that any other points on that interval could be higher. Let me just show you that on the calculator too. So if we have this in our calculator, I'd want to be looking at x squared plus 2x minus 4. But I only want to look at it between -1 and 1. There's what it looks like over -10 to 10. But if I just look at it from -1 to 1, that's the only piece of the graph I'm looking at. And I can see that my absolute lowest point is right here at the beginning. So at -5, that's where I have my lowest point. And my highest point is right there at the other end. And that's at -1. So I can check my work on the calculator. All right, same thing on this one. We're going to take our derivative, set it equal to 0. So I have to use the quotient rule. Derivative of the top is 1 times the denominator minus the numerator, derivative of the denominator, all over the denominator squared. That gives us this. Remember, our critical numbers occur wherever we have the derivative equal to 0 or wherever we have the derivative undefined. So you should be thinking, well, we have a critical number at x equals 2. But if we look back at the original function, this has a vertical asymptote at x equals 2. If we have a vertical asymptote, we can't have a high or low point because we don't even have a function. So therefore, we do not have a critical number at x equals 2. Also, 2 is not even in this interval that we're looking at. We're only looking from 3 to 6. So we know the only possibility is that the extrema have to occur at the endpoints. So I'm going to check g of 3, plugging 3 in. I'm going to get 3. Plugging 6 in, I get 3/2. So this is the highest, this is the lowest, so therefore we have an absolute max at 3, 3, and we have an absolute min at 6 3/2. So again, just going through this again real quick, this was all about finding extrema. Extrema can be high points or low points. We took it one step further to the extreme value theorem, which says if we have a closed interval, we have to have an absolute highest or lowest point. We then reviewed how to find critical numbers. Critical numbers occur when that derivative is 0, because that's where the slope is going to be 0. The slope is going to be 0 at high points or low points. So after we found those critical numbers, then we took it even a step further. We said when we're finding the absolute extrema, those can occur at either the endpoints or the critical numbers. And it just so happened on these that we really didn't have many critical numbers to check. We just had to check those endpoints.